Today we are walking through the paper titled Generative Recursive Reasoning.
What problem is the paper trying to solve?
The paper asks how neural reasoning systems should spend extra computation. Existing recursive reasoning models refine a hidden state over and over, but they usually follow one deterministic path and end at one answer.
So the weakness is not recursion itself. It is that the recursion collapses to one root.
Exactly. The paper calls out cases like in-queens and graph coloring, where the same input can have many valid solutions. If a model always takes one latent truth, it can miss other valid answers or get trapped in a bad refinement path.
What does GRAM change in that setup?
GRAM turns recursive reasoning into a probabilistic process. Instead of updating the latent state to one fixed next state, it samples a reasoning trajectory. Multiple samples become multiple attempts to solve the same problem. The method diagram shows the main move. GRAM keeps a low-level state for fast refinement and a high-level state for the slower reasoning trajectory.
Which part of the diagram makes the reasoning stochastic?
First, the low-level block repeatedly refines detailed computation. Then the high-level block proposes an update. GRAM adds a learned random guidance term to that proposal, so two runs can explore different high-level directions while still using the same deterministic refinement machinery. Here is the compact equation for that high-level update. The new high-level state equals the deterministic proposal plus stochastic guidance.
Is the noise just random shaking, or is it learned?
It is learned. The prior predicts a distribution for the guidance from the current proposal, while the posterior sees the target during training. That variational training teaches the prior which directions are useful before the target is available at test time. This equation is the broader transition view. The next latent state is sampled from a distribution conditioned on the previous latent state in the encoded input.
How does that help at inference time?
Deterministic recursive models can mostly scale by running deeper. GRAM can also scale wider. Sample many trajectories in parallel. Decode their candidate answers. Then choose by majority voting or a latent process reward model. The trajectory illustration shows the intuition. Prior recursive models collapse 3 runs into the same path, while GRAM lets different runs reach different valid solutions.
The important contrast is same input, same deterministic path, versus sample paths that can split?
Yes, that is why the paper evaluates both hard single-answer reasoning on multi-solution constraint tasks. The point is not just to get one answer, but to avoid collapsing the whole solution space too early.
What happens on the main reasoning benchmarks?
On Sudoku Extreme, GRAM reaches 97.0% accuracy. That is above TRM at 87.4%, HRM at 55.0%, and Loop Transformer at 61.3%.
Does the same pattern hold on ARCAGI?
Against the controlled recursive baselines, yes. On ARCAGI1, GRAM gets 52.0% versus TRM at 44.6% and HRM at 40.3%. On ARCAGI2, GRAM gets 11.1% versus TRM at 7.8% and HRM at 5.0%. The gray bars are large language model reference points, not controlled baselines. They show that ARC remains difficult, while the main apples-to-apples claim is that stochastic recursion beats deterministic recursion under similar recursive model settings.
Where do they show the new width scaling idea?
The left panel varies both iterations and the number of parallel samples on Sudoku Extreme. GRAM improves as it gets more samples, and with 20 samples at 16 iterations it reaches 97.0%. Above deterministic baselines run for 320 iterations, including TRM at 90.5%.
And the right panel is about many valid solutions.
Right. As the number of valid n-queen solutions grows, Loop Transformer, HRM, GRAM with one sample stays near the top because its learned stochastic transition is less tied to a single deterministic attractor.
The paper also calls GRAM generative. What is generated besides answers?
They test unconditional generation too. For Sudoku, GRAM starts from an empty board and generates complete boards. It achieves 99.05% validity over 100,000 samples, while the strongest D3PM baseline reaches 91.33% with many more parameterizing steps.
So the generative claim is not only about diversity, it also has to satisfy hard constraints.
Yes, the paper emphasizes validity and uniqueness together. High validity alone could come from repeating a few boards, but the reported valid Sudoku samples are unique under exact board matching. On VOICEVOX NIST, the qualitative picture is recursive refinement. D3PM denoises across many steps, TRM stays stuck, and GRAM sharpens recognizable digits over 16 recursive steps.
What limitations should viewers keep in mind?
The authors note that deep supervision is sequential, so training is less efficient than standard transformers. That matters if GRAM is scaled toward larger foundation model settings.
Then what is the final takeaway?
The takeaway is that recursive reasoning does not have to mean one hidden path. GRAM makes the path probabilistic, so a compact recursive model can explore alternatives, scale by both depth and width, improve over deterministic recursive baselines, and even generate constrained structures from scratch.
That makes the contribution clear. The paper adds exploration to recursive reasoning, instead of only adding more recursion depth.
That wraps up this paper walkthrough.